With Unit 2 in this video, and for the next couple learning targets we're going to be focusing on how to solve quadratic equations using a variety of methods. And in this video we're going to focus on learning target 4C part 1, which is how to solve quadratic equations either if we're given a graph or by using square roots algebraically. So a quadratic equation comes from our quadratic function, and in learning target 4A we learned about what a quadratic function looks like in both vertex form and standard form. And a quadratic equation uses the standard form of that, which is ax squared plus bx plus c. And instead of this being equal to y, we're setting this equal to 0 because we're solving this quadratic equation now. And of course, a cannot be equal to 0 since we have to have that x squared term, otherwise we don't have a quadratic then. So there are lots of ways to solve quadratic equations, and in this learning target we're going to look at 3 different ways, and in this video we're going to look at both graphing and square roots. And I do want to make the added statement here that square roots only work if our b term is equal to 0, and that b term is our middle term here, meaning that I would have no x term, I would just have an x squared and a constant term. And as we learn about different methods, we are going to have some restrictions like this because unfortunately not all methods for solving quadratic equations work for all quadratic equations, and that's why we have a couple methods that we'll be learning. Now before we jump into learning how to get our solutions from graphing, I do need to talk about a little vocab. So solutions for quadratic equations have lots of names that all mean the same thing. So solutions, roots, zeros, and x-intercepts are all the same thing. And if we're trying to solve a quadratic equation by looking at a graph, what we're ultimately looking for are those x-intercepts. And the reason that's happening is because when we have x-intercepts, that's happening because we set y equal to 0. And if we look back up here at our quadratic equation, we were used to this ax squared plus bx plus c, but instead of it being equal to 0 before, we had this equal to y. Well, when we're solving this, we set this equal to 0 because we're setting y equal to 0, which is the same thing that we would do to find our x-intercepts. Which is why when we're solving for something on a graph, that is the exact same thing as finding the x-intercepts. 2 other names that we're going to see not only in this unit but also for the rest of the year is roots and zeros, and those 2 mean the same thing as solutions, which are our x-intercepts on our graph. So let's look at our first example here. We want to find all the solutions for the graph below, and I want to remind you guys that those solutions are the same thing as our x-intercepts. So although it doesn't say specifically find the x-intercepts, by saying that we want to find the solutions for the graph means that we are looking for the x-intercepts. So I want you guys pause the video and write out what our x-intercepts are going to be. So looking at this graph, I can see that I have 2 x-intercepts that I'm going to circle here. I have it at -2 and I have it at x equals +2. Now in our last unit I was very particular about having us write x-intercepts as coordinate pairs, so if we're thinking about these as x-intercepts, our answer would be 2, 0, and then -2, 0 for the negative answer. But since they didn't technically ask us to find the x-intercepts and they just said find the solutions, it would be okay to just list these as x equals 2 and x equals -2 as our answer. Let's look at our next graph. So in example 2 here, instead of saying find the solutions, it says find these zeros for the graph below. Well again, our zeros up here are the same thing as our solutions. So we want to go ahead and find the x-intercepts on this graph. Would you guys pause the video and find your zeros for the graph below? So again, our zeros mean our solutions, which is the same thing as our x-intercepts, and I have 2 on this graph. I have them at 2, 0 as well as 4, 0. But since they asked for the zeros, technically I could list them as just x equals 2 and x equals 4. Now of course if you want to list them as the full coordinate pairs with the x-intercepts, that would be correct as well. So either of these answers would work. Let's look at our third example. So here we see that we're getting another vocab word introduced. It says to find the roots for the graph below. Now just like we saw up above in that list, solutions, zeros, roots, and x-intercepts all mean the same thing. So when they ask us to find our roots, they're really asking us to find our x-intercepts. Why don't you guys pause the video and find our roots for this graph below? So for our roots, I'm looking for our x-intercepts. I only happen to have one on this graph, and that can happen sometimes. So I just have one x-intercept at 0, 0, or I could list that as just x equals 0. And we're going to see throughout this section that when I have a quadratic equation that I'm solving, that for a lot of them I'm going to end up with two answers, and we're going to see some cases where I maybe only end up with one answer, or I end up with no answers at all. But what we are not going to see is we're never going to see more than two solutions. So for a quadratic equation, since our highest power is that x squared, that means that I can have at most two solutions then. So in a lot of cases we will see two solutions, but just like in example 3 here, we might just have one solution. Let's look at our last graph example. So here in example 4, it says to find the zeros for the graph below. Why don't you guys pause the video and answer example 4 on your own first. So to check example 4, again, our zeros are asking us for our x-intercepts. And in this case, when I look at the graph, my parabola is completely above the x-axis and it is facing upward. So we know that since this parabola graph is a U-shaped, it's never going to curve and come back down. So I actually have no x-intercepts then. What that tells me then is that I have no solutions, or specifically, I have no real solutions. And the reason I'm throwing that extra word in there of no real solutions is later on towards the end of this unit, we're going to actually look at something called imaginary and complex numbers. And eventually we're going to have a solution for this. It's just not going to be a real number. Instead, it's going to be what we call an imaginary number. And that's going to be something that we look at in a couple learning targets from now. Okay, let's look at our last method for this video. So our last method here is we're going to solve the following quadratic equations by using square roots. And again, I want to emphasize that this only works if our b term is equal to 0. So when I have this general quadratic equation of ax squared plus bx plus c, and it's set equal to 0, this only works if I don't have this middle term here, which is that x term. And if I look at examples 5 through 8, we'll see I just have the x squared and a constant term in all of these. So there's no linear term here. Now our goal with using square roots is that we want to isolate the square root, or our goal with using square roots is we want to isolate the x squared term first, and then what we're going to end up doing is applying a square root to both sides. So let's look at example 5. We have 3x squared minus 75 equals 0. We want to isolate that x squared term, so I can add the 75 over. Then from there I can divide through by 3, and we get x squared equals 25. Now here I've isolated the x squared term. Once we isolate the x squared term, I want to get rid of that square, and I can apply a square root since the square and the square root cancel. Whatever I do to one side, I have to do to the other side as well. So I'll apply a square root to both sides. Now on the left side, the square root of x squared is just going to be equal to x. And on the right side, when I apply a square root to a number, I have to remember to put a plus or minus sign in front of it. So what I really have here is this, is that x equals plus or minus the square root of 25. Now, if we can reduce down the square root, we want to continue to reduce it down as much as we can. In this case, 25 is a perfect square, and the square root of 25 is equal to 5. So I'll end up with x equals plus or minus 5. And this does really mean that I have two answers. This is saying that x equals 5, and x is also equal to negative 5. If we would like to shortcut it and write the plus or minus, you are more than welcome to. If you would like to list them as two separate answers, you could do that as well. Let's look at example 6. So in example 6, we have 4x squared plus 16 equals 16. I don't have an x term, so I can use square roots. Again, my goal is to isolate that x squared term. So why don't you guys pause the video and isolate that x squared term. So to isolate our x squared term, I'm going to subtract the 16 first, and we'll have 4x squared equals 0. I can now divide through by 0, and I get x squared equals, well, 0 when I divide through by a non-zero number, such as 4, that's going to be equal to 0. So I get x squared equals 0. Now that I've isolated my x squared term, I want to go ahead and apply the square root to both sides. Don't forget about that plus or minus on the side with the numbers. Now the square root of x squared is just equal to x. We end up with x equals plus or minus the square root of 0. We can continue to simplify down that square root. The square root of 0 is just 0, and I end up with x equals plus or minus 0, but since there is no difference between positive or negative 0, I just end up with one answer in this case of just x equals 0. Let's look at example 7. We have 3x squared plus 27 equals 0. Why don't you guys pause the video and solve example 7 on your own first using square roots. So let's check example 7. So the first thing I need to do is isolate that x squared term. So I'm going to subtract the 27 over, then divide through by the 3, and I get x squared equals negative 9. Now that my x squared term is isolated, I can go ahead and square root both sides. And I want to remember that plus or minus on the number side. The square root of x squared is just equal to x, and I end up with x equals plus or minus the square root of negative 9. Well, what's the square root of negative 9 going to reduce down to? Well, I actually cannot take the square root of a negative number, and because I cannot take the square root of a negative number, this is actually giving me no solutions, or specifically no real solutions. So this is similar to that example up above where the graph didn't intersect the x-axis. And if we were to actually graph the function 3x squared plus 27, this graph would also not intersect the x-axis. And the reason I can see that is I have a stretch by 3, and I also am shifting this graph up 27. Now this graph is facing upwards to begin with, so when I stretch by 3 and move it up 27, I have a graph that's completely above the x-axis, and I have no x-intercepts here, which matches up with the fact that I got no real solutions when I tried to solve it algebraically. So one thing we are going to keep in mind as we learn about all these different methods for solving quadratic equations is that we can use a different method sometimes. I could have solved by graphing if I wanted to graph any of these, and in some cases maybe I could solve by square roots, and as we learn other methods we could use those to check our answer as well. We're going to start to see the connections between them where we have the cases with 2 solutions, 1 solution, or no real solution. And as I hinted to earlier, eventually in this unit we will be able to find the answers specifically, and we won't keep saying no real solutions for something like example 7. And once we learn about our complex and imaginary numbers, we will actually be able to get that imaginary answer that there is. Let's look at our last example here. So in example 8, we have 2x squared minus 24 equals 0. Why don't you guys pause the video and solve example 8 on your own first. So to solve this guy, my goal is to isolate the x squared. So I'm going to go ahead and add 24 to the other side. Then I can divide through by 2, and we get x squared equals 12. Now that the x squared term is isolated, I want to square root both sides. Don't want to forget about that plus or minus. So I end up with x equals plus or minus the square root of 12. Now here 12 is not a perfect square, but 12 does have perfect squares inside of it. 12 can factor as 4 times 3, and 4 is a perfect square. So we can continue to reduce down this answer and break this apart as the square root of 4 times 3, which would give us x equals plus or minus 2 root 3. Since the square root of 4 is 2, I can take that 2 out of our square root and end up with 2 times that square root of 3. I don't want to forget about that plus or minus either. So sometimes we get these perfect squares like we did in example 5 where we had the square root of 25 and we're able to reduce it down all the way. Other times we might not get exactly a perfect square, but if we can continue to reduce it, we'll want to keep reducing it down as far as we can. And that's not going to just go for when we're solving using square roots, but we're going to see this in other sections as well as we continue to move on in this unit.